Welcome to the debate. Today, we're delving into one of the really big mysteries in cosmology, dark matter. I mean, this invisible stuff is thought to make up something like 85% of all the matter in the universe. We can't see it, but we infer its existence mainly from, well, overwhelming gravitational evidence pretty much everywhere we look across all cosmic scales. But, its actual nature, what is it? And what's the best theory to describe it? That's still very much up for grabs, scientifically speaking. So our central question today, the core of our debate, is this. The standard dark matter hypothesis has a lot going for it. It's widely supported, sure. But is it really comprehensive enough? Does it explain everything we see? Or do we need maybe more nuanced, perhaps broader frameworks, like the dark plasma theory, to get a more complete picture? My position is essentially that the standard hypothesis, which keeps getting refined and has piles of converging evidence behind it, is still our most robust and consistent explanation for all these gravitational anomalies we observe.
Right, and I'm coming at this from, let's say, a slightly different perspective. While I absolutely acknowledge the power and the successes of the standard model, I do think it might ultimately be incomplete. My argument is that we probably need a more, expansive framework, one that actually integrates some diverse ideas, including things like the dark plasma theory you mentioned. I think these alternative views offer some really crucial insights into what dark matter is and how it behaves, potentially giving us a fuller understanding of this whole cosmic puzzle.
Okay, so to start, let's just lay out the case for standard dark matter. The evidence is really quite compelling. It's not just one thing. It comes from many different independent lines of inquiry, and they all sort of cross-correlate and point towards the same conclusion. Dark matter seems to be real. And when you compare the standard hypothesis to alternatives like modified Newtonian dynamics or MOND, the standard model just consistently does a better job across a huge range of scales and situations. Take Newton's second law, for example, F equals ma. It's been tested experimentally down to incredibly low accelerations, way lower than the level where MOND predicts gravity should start behaving differently. And recent studies, really precise ones, using data from the JWST satellite looking at wide binary stars, they seem to directly contradict MOND's basic idea. Supporter of MOND has said publicly that these results are, quote, strongly against MOND. He observed no breaks in the gravity law right where MOND expected them. And it's not just that. MOND really struggles to explain how ultra-faint dwarf galaxies behave, these tiny spread-out galaxies, and also the dynamics within huge clusters of galaxies. So it seems to have problems at both the very small and the very large scales. It also, it runs into issues explaining the early universe. It has trouble predicting gravitational lensing accurately, and this was a big one. It incorrectly predicted that light and gravitational waves would travel at different speeds. We had those sensitive experiments in 2015 and 2017 that absolutely confirmed their speeds are identical. That was a significant blow for MOND. But maybe the most sort of visually striking evidence against MOND, and honestly, many modified gravity ideas, came from observing the bullet cluster back in 2006. That was just groundbreaking. It showed pretty undeniably, I think, dark matter existing separately from the normal visible gas. You had these two galaxy clusters colliding, right? The ordinary matter, the gas, smashed together, heated up, slowed down. But the bulk of the mass, inferred from lensing, just passed right through without interacting. That's a clear separation. It's exactly what you'd expect from collisionless dark matter. But it's incredibly difficult for any theory that just tries to tweak gravity to explain without adding some kind of invisible mass. Oh, and one more thing. There's this satellite galaxy of NGC 1052. It seems to have almost no dark matter at all. And guess what? Its stars orbit slowly, around 8 kilometers per second. Those like standard Newtonian physics predicts, without dark matter. Not the 30 kilometers per second you'd expect if dark matter was there, or if MOND's rules universally applied regardless of dark matter. MOND predicts rotation speeds based on the visible matter in a way that shouldn't really care if dark matter is there or not, but this galaxy clearly contradicts that. And finally, just wrapping this up, The standard model does a much better job explaining the patterns, the anisotropies in the cosmic microwave background radiation, the Big Bang's afterglow, and how large structures like galaxy clusters formed over time. MOND really struggles to model those early density fluctuations correctly.
Okay, I hear all that. And look, I absolutely agree that MOND faces some very significant, maybe even fundamentals problems. The bullet cluster, the gravitational wave speed, those are serious challenges, no doubt about it. Its limitations are pretty clear. However, even with those flaws, I think MOND, and maybe other alternative ideas too, they offer some useful insights that let's say, a broader framework could potentially incorporate, rather than just throwing them out entirely. For example, MOND, even though it gets the amount wrong, it does highlight that you need some kind of invisible mass component to make sense of the observations. And this idea that maybe some of the missing mass isn't perfectly collisionless, that it could be self-interacting dark matter, that's actually already part of the wider dark matter discussion within the standard model community now. It's not necessarily a rejection of dark matter itself. So this is why I lean towards advocating for a more comprehensive picture. Particles. What if it's actually a kind of plasma? A plasma made of particles that do interact with each other, albeit weakly, and maybe even carry a slight charge. Now, this isn't necessarily throwing out the standard lambda CDM model entirely. On large scales, it could still be consistent with it, but on smaller scales, it aligns well with these self-interacting dark matter, or SIDM models. So the idea is that it could potentially bridge these different scales and different approaches, and a dark plasma, well, it could behave in all sorts of complex ways, depending on the conditions, like a liquid crystal, a fluid, even a superfluid or a supersolid. And we do see simulations, like Christian Spethman's work, showing this kind of fluid-like behavior emerging. And there are actually quite a few interesting parallels between this idea of a dark plasma and superfluids. You can study both using magnetohydrodynamics, MHD, the physics of conducting fluids and magnetic fields. Both might exhibit something like zero resistivity, similar to superconductivity. Superfluidity itself often comes down to identical quantum mechanical behavior, right? Well, it's conceivable that a dark complex plasma, perhaps involving hypothetical things like supersymmetric cue balls, these stable charged lumps, could also achieve this state. And here's a really key point. It doesn't necessarily have to be super cold. Simulations of these cue balls forming and studies looking for them in high-temperature plasma at places like CERN suggest they could be stable at pretty much any temperature. So this challenges that common picture of superfluids only existing at near absolute zero. I mean, we see transient superfluid plasma in liquid helium experiments. There's talk of Bose-Einstein condensates of photons in high-temperature plasma, neutron Bose-Einstein condensates in hot neutron stars. Even the quark-gluon plasma right after the Big Bang could be considered a type of superfluid. So superfluidity might not be just a cold thing. And there are actually quite a few interesting parallels between this idea of a dark plasma and superfluids. You can study both using magnet hydrodynamics, MHD, the physics of conducting fluids and magnetic fields. Both might exhibit something like zero resistivity, similar to superconductivity. Superfluidity itself often comes down to identical quantum mechanical behavior, right? Well, it's conceivable that a dark, complex plasma, perhaps involving hypothetical things like supersymmetric cue balls, these stable, charged lumps, could also achieve this state. And here's a really key point. What's more, a dark plasma would naturally generate acoustic waves, Elfin waves, which are specific to plasmas. It inherently has long-range correlations that's a defining feature of any plasma. And if you spin it, it develops vortices, just like Corey notes for superfluids, and just like we see in regular plasmas. So what I'm suggesting really is that maybe the superfluid theory, while valuable, could actually be seen as one aspect, one component of this broader dark plasma hypothesis. It might offer a way to unify these different observed behaviors and interactions under one sort of larger umbrella.
That's certainly a very rich theoretical picture you're painting, and I appreciate the attempt to synthesize these different ideas: superfluid, self-interaction, plasma physics. It's ambitious. However, I'm still not convinced that these alternative frameworks really offer more explanatory power than the standard lambda CDM model, especially when you consider the standard model's own ability to adapt and incorporate new findings. Nor am I convinced they present fewer theoretical hurdles, frankly. Lambda CDM, cold dark matter plus a cosmological constant, it has this remarkable track record of integrating new data, even data that initially looks like a major problem, an anomaly. Take the James Webb Space Telescope, JWST, findings about early galaxies. You're right. Initially, they looked weird. Too bright, too big, too massive for how early they were in the universe's history. And yes, people immediately started questioning the Standard Model. But what happened? Well, further research, detailed simulations published in places like the Astrophysical Journal letters, including work from Northwestern University, they showed that something called bursty star formation could explain it. These short, really intense periods of stars forming and dying can make less massive galaxies shine incredibly brightly for a while, making them look more massive than they are. So these findings ended up being consistent with standard cosmology after all. It just meant we needed to adjust our assumptions about how stars formed back then, which isn't unreasonable. And then there was that other piece of the puzzle, the 2024 study by Chuarovsky and others. They found that some of those impossibly large early galaxies appeared that way partly because their central black holes were gobbling up matter so fast. This process creates friction, pumps out a lot of heat and light, and basically creates an optical illusion, puffing up their apparent size. They called them little red dots. Once they accounted for those specific objects and removed them from the sample, guess what? The remaining galaxies fit right within the standard lambda CDM predictions. So this shows the Standard Model being refined and adapting, not failing. So while the conceptual elegance of superfluids or dark plasma is definitely appealing, the Standard Model just keeps providing a more robust, more consistently verified picture across the board. And those problems with the other alternatives, they haven't gone away. Emergent gravity, for instance, it's been shown to be even less effective than MOND for galaxy rotation and worse than the dark matter hypothesis for galaxy clusters. Primordial black holes? As an explanation for all dark matter, that idea is pretty much entirely ruled out according to studies by Siracqua and Loeb, based on things like the dynamics of our own Kuiper belt and the fact that tiny black holes would have evaporated via Hawking radiation ages ago. Even the superfluid dark matter theory you mentioned, while interesting conceptually, it behaves just like normal fluid in galaxy clusters, which means in those huge structures where dark matter's influence is most critical, it, as Sabine Hassenfelder pointed out, does not add anything to our understanding, which the standard dark matter hypothesis couldn't already tell us. She also noted it has incomplete equations. So the Standard Model, it just seems to keep weathering these storms and explaining more consistently.
Okay, that's a very fair defense of the Standard Model's adaptability. And yes, the work explaining the JWST data through bursty star formation and those AGN optical illusions is definitely valuable. It shows the model can incorporate more complex astrophysics. But see, I might frame that slightly differently. I'd argue those reconciliations are precisely about adding more complex physics into the standard framework, which is fundamentally what the dark plasma idea is suggesting on a potentially deeper level, looking at the particle physics, the interactions. So maybe it doesn't invalidate the need for a broader scope, but actually reinforces it. It suggests the Standard Model still needs to expand, particularly when we think about potential particle interactions and, crucially, the limitations of how we're currently looking for dark matter if we want to get the full picture. For instance, you mentioned bursty star formation explaining some JWST results. Okay, but it's also plausible that self-interacting dark matter could play a role in accelerating galaxy evolution. There's work by Julian Munoz and Avi Loeb suggesting that if dark matter particles can interact weakly with normal matter, maybe through some small charge, they could have helped cool hydrogen gas way back in the dark ages, before the first stars. That cooling would speed up star and galaxy formation. And interestingly, that kind of interaction might also help explain those puzzling signals from the EDGES experiment, that unexpectedly strong hydrogen absorption signal from the early universe, which is still a bit of a headache for the standard picture. So this points towards interactions beyond just gravity, which is exactly what a dark plasma model incorporates. And this brings me to maybe my main concern right now, the somewhat, dare I say, simplistic nature of many of our current experiments designed to directly detect dark matter.
They are, let's be honest, largely fixated on WIMPs,
weakly interacting massive particles. That's just one category of candidate. And this focus means they often just completely ignore self-interacting dark matter particles, which would be the constituents of a dark plasma. Our experimental designs might not be sensitive to different fundamental forces that could be involved, or the possibility that dark matter lives in different dimensions, or maybe even has different fundamental symmetries like parity or time reversal in these hidden dark sectors. What if, for example, some supersymmetric dark sector particles have reversed parity compared to ours? Our detectors might be looking for the wrong mirror image and would simply miss them, not because they don't exist, but because of how we're looking. And this brings me to maybe my main concern right now. So the conclusion I draw from this is that yes, new particles, meaning new kinds of matter, seem necessary to explain a lot of observations and to complete our theoretical models. The standard dark matter hypothesis is one way to incorporate one kind of new particle, and it's been very successful, I grant you that. But all these hints of complexity, the potential for interactions, the theoretical possibilities, they suggest new hidden universes or sectors. They imply a much richer, undiscovered layer of physics that a framework like dark plasma is trying to conceptualize. Finding it, well, that's going to be tough. It might take a lot longer, because we probably need to broaden our search strategies way beyond the current, perhaps limited assumptions we've been making.
So we've journeyed through this complex landscape of dark matter, starting from the really solid evidence that something unseen is out there, shaping the universe, and moving into the intricate details and debates around different theoretical explanations. For my side, I've emphasized the, I think, remarkable explanatory power and the sheer consistency of the standard dark matter hypothesis. It's shown itself to be surprisingly resilient, successfully incorporating new, initially puzzling observations like those from JWST, while alternative ideas like MOND or emergent gravity continue to face pretty significant persistent challenges. The way the standard model gets refined, dealing with things like bursty star formation or black hole effects, really highlights its adaptability and why it remains, for now, the most comprehensive and scientifically validated picture we have.
And from the other perspective, I've put forward the case for striving towards a potentially more comprehensive understanding. While fully acknowledging the standard model's many successes, I've argued that ideas like the dark plasma hypothesis might offer a richer, more integrated way forward. By bringing in concepts like superfluidity, allowing for diverse dark matter interactions, and potentially bridging different observational scales, it aims for a broader synthesis. And this view also raises critical questions about our current experimental methods. Are they perhaps too narrowly focused? It emphasizes that the universe's complexity likely demands we consider new kinds of particles, new interactions, maybe even new physics, to truly get to the bottom of the dark matter mystery.
Well, this discussion certainly highlights just how complex understanding these unseen parts of our universe really is. It's a fantastic illustration of the scientific process itself. Dynamic, challenging, always evolving. Both viewpoints, I think, show the depth of thought going into this truly fascinating puzzle.
Absolutely. And the path forward to really figuring out what dark matter is, it's undoubtedly going to involve more rigorous observation, continued theoretical innovation, and crucially, keeping an open mind to these diverse perspectives and possibilities. There's clearly so much more to explore here, a lot more work to be done.